All right, guys. So maybe to kick it off, you can introduce yourselves.
Yeah. I'm Karan. I'm the co-founder and CEO of K2 Space.
Neil, the engineering brother in the family, the CTO and co-founder.
Amazing. And how'd you guys pick the name K2? Because I imagine a lot of people have the wrong idea there.
Yeah, it's pretty funny. There's like multiple meanings for it, but the core primary reason is a Type 2 Kardashev civilization, which is this like amazing sci-fi concept that a civilization that reaches Type 2 Kardashev is one that's able to build giant structures in space. The hallmark of a K2 civilization is one that can build a Dyson sphere, a giant ring around the sun that collects unlimited renewable energy. And so our whole thesis is the future is bigger.
When you started the company, the consensus was going towards building smaller satellites. And you guys took this bet towards building bigger. Maybe explain how you came to that.
We started K2 on a contrarian bet 4 years ago. While everyone else was building smaller when it comes to space, we thought that the future was building bigger. We're building the largest, highest power satellites that have ever been created.
Physics really wants satellites to be bigger, right? So from a payload perspective, all of the mission performance comes down to a combination of three things: power, aperture, which is essentially the size or volume of the payload, and mass. Those three things define every satellite mission performance budget. And so instead of trying to shrink down the size of our satellites where you'd get less power, you'd get smaller apertures, you'd get less payload mass, we wanted to go in the opposite direction and give our customers really what the mission demands, which is more power, more aperture, and more mass. Now, that's a really hard engineering challenge, right? To do that at a super low cost, almost equivalent to those smaller satellites. It's why nobody had ever tried to do it before, but we thought if we could solve that engineering challenge, we'd be the first to offer that kind of product to the market.
And speaking of that, I think it's probably underappreciated the engineering work you guys have taken on over the past few years. So maybe just talk about some of the challenges that you overcome to build the Mega.
Yeah, so this class of satellite really comes down to three core challenges: propulsion, power, and radiation. So on the propulsion side, legacy high-power satellites use these things called Hall thrusters to move around in space. Usually they're these ion thrusters that operate at around 1 to 2 kilowatts of power, maybe 4 kilowatts of power max. Our Hall thruster is a 20 kilowatt Hall thruster, so 4 times as high power as the highest power Hall thruster that's ever flown previously. To design that kind of system requires a lot of very specialized expertise. That's why we have Rafael Martinez, our head of propulsion, who designed Starlink's Hall thrusters, has more Hall thrusters in space than really anybody in history. He is the one who came in to design that system. And that system is core to how we get around in space. With a massive vehicle with this much power, we need to be able to move around on orbits very flexibly, and the Hall thruster allows us to do that. The second challenge is power, right? So in space, the only way to increase your power is to increase the size of your solar arrays. So in order to develop a high power satellite, we had to build gigantic solar arrays with really complex deployable mechanisms and operate extremely high voltage power systems, right? And that, combination of challenges is extremely hard. People have done it before, but usually it takes exquisite engineering, extremely high cost, decades to solve these. We did that at a very low cost in the span of just a few years. And the final challenge is radiation, right? If you're building a small satellite in low Earth orbit, radiation's pretty easy, right? That's why most of the Starlink satellites operate in that regime. A lot of low-cost satellites tend to go there. But if you're going into the higher orbits, medium Earth orbit, GEO, cislunar space, deep space, radiation becomes an immediate problem. We've had to be very careful about every circuit that we use, every amount of testing that we do. We do millions of dollars worth of radiation testing to make sure our parts can survive in those environments. And that's been, core to all of our electronics design from the very beginning of this company. So solving those three problems, at a low cost, at very, very fast pace, is really what our engineering team was built to do.
2026 has already been a mega year for K2. Maybe just talk about some of the milestones that you've already hit.
Yeah, so it's been a really incredible year. This year we announced our first big commercial win, a 100 satellite commercial deal with a company called SES. It's one of the largest commercial satellite deals in the industry. We announced our first big national security win, followed by 2 others. We've now stacked a number of wins across different orbits. And of course, as everyone knows, we had our first big satellite flight, a mission called Gravitas, where we started to test out and de-risk the full end-to-end platform.
Maybe just talk about what that mission validates for you.
Yeah, so it's the first time all of our in-house systems are coming together. To build a satellite of this class, you have to be extremely vertically integrated, right? You have to build all of these different subsystems in-house, and this is the first time they're ever in space and also operating together. So it's the first time we were testing our system, putting it through its paces, really making sure all of those subsystems work. So that includes the deployable solar arrays, propulsion systems, avionics systems, and most importantly, making sure our payloads work. So on this mission, we carried 12 payloads up to space for a variety of partners and customers, and we wanted to make sure that we could deliver on their data and activate them successfully. So all of those things we tested out together, along with our flight software, our ability to update that flight software on orbit, and most importantly, our ability to operate a satellite in space.
And you're seeing a massive inflection today when it comes to national security. Maybe just talk about how space is becoming increasingly important and how K2 fits into that future.
Yeah, we're in an interesting scenario where almost every application today relies on capabilities from space. Like people don't realize, um, everyone relies on 32 GPS satellites sitting at 20,000 kilometers. So developing space architecture that is resilient is incredibly important. In the last 90 days, we've announced wins with national security customers across every orbit. We announced that we won Golden Dome space-based interceptors, partnering with Anduril, where we're the host spacecraft vehicle for a constellation in LEO. We announced that we won a missile warning, missile tracking contract with the U.S. Space Force in MEO. And we announced that we won our first program of record for a program called PTSG with the U.S. Space Force, where we're providing a military SATCOM capability in a way that's never been done before.